So it's a pleasure to see everybody here today, and a real pleasure to introduce Ari Socrates. Ari is an absolute legend in theoretical astrophysics. He did his PhD work with Omer Blaise, I believe, in Santa Barbara, finished in 2004, got a Hubble Fellowship, went to Princeton for a while, and then he became a John Bacall long-term member at the Institute for Advanced Study. And I was there around that time, as I remember, and Peter Goldreich was sort of taking you under his wing. But in any event, Ari eventually decided to leave astrophysics and went and worked in a series of startups, and I think it's done very well, and is now at Camber, which we'll hear about today. So Ari, welcome.
Okay, thank you, Charles. Appreciate it. So I'm giving everybody a little bit of a warning. This is the first time I am giving the talk as a CEO of a company that makes a product for researchers to researchers. So let's see how this goes. So as Charles gave a great introduction, thank you for that, Charles. I am a former astrophysicist. I worked in a lot of different areas, planets, MHD, supernova gamma ray bursts. Worked with a lot of great people at a lot of great places. And about 10 years ago, I made the decision to move to the tech sector in the Bay Area with my family. And I've been working at startups ever since. A year and a half ago, I started this company called Camber. And we closed our first round of funding in June. And basically, what Camber is a cloud computing platform for scientists. And not just any scientists, but for particular fields of science. So astrophysics, genomics, physical chemistry, so on and so forth. And so I think for people in science who are primarily working on premise, maybe the first thing to address is what is the big deal about the cloud? Like, why is the cloud a big deal or even a thing? And so, it's a complex question with a lot of players. It's a complex system. And in physics or in nature, when you're looking at a complex system, in order to understand the individual constituents, you look for the flow of energy. So this is the first law of thermodynamics. I hope I got that right. Did I get the minus and plus signs correct? And in the business world, instead of following the energy, you follow the money. And so this is the revenue of Amazon Web Services, AWS, from 2006 to 2022. Actually, today the revenue, I just found this on the internet, the revenue of Amazon Web Services today is not $71 billion a year. It's more like $110 or $120 billion a year. So this plot, in my opinion, really encapsulates the most important trend in technology in the last 10 years. And basically, there's not only Amazon Web Services, but there's a few other players, mostly two other players. So the Google Cloud Platform and Microsoft Azure, they're all basically carbon copies of one another. And then those are called the public cloud. So anybody with a credit card can go use the public clouds. There's also what I would call the private clouds. So very large tech companies like Amazon, Google, and Microsoft of that same scale, and in some cases themselves, have an internal private cloud for doing all their stuff. So for example, Facebook has an internal private cloud that's of order the size of AWS, but it's only for them. This has really completely changed the makeup of the technology sector in the last 10 years. Really, it's changed what you can do. And the real sort of upshot is that small companies can do relatively big things. And so, how did this happen? So again, it's follow the money. So how this really happened is because a company like Amazon has a lot of money. and that they can buy a lot of stuff. And so this is an AWS data center. I think this is in Oregon or something like that. That's one data center for AWS in Oregon. In Oregon, they have 6 or 7 of those. And in the world, they have hundreds and hundreds of these. And so what this allows them to do is to basically have effectively an infinite amount of capacity that is not being used, to be frank. That's actually just sitting there dormant. So that they can allow any customer to have an on-demand experience and absorb the fluctuations in usage so that everybody can have this on-demand instant experience. So there's no waiting in a queue or anything like that. So because of this, what has happened in the tech sector is that the adoption of the cloud, or the initial adoption of the cloud, maybe in the 2010, 11, 12 era, allowed for there to be a common developer platform where very sort of creative, intelligent, like ingenious people could have their open source frameworks for doing distributed computing or big data processes, work on these platforms sort of out of the box, and then you can have a community of people come in and contribute to that code base and get community support of people using this. So we don't have to explain what all these things are, but they're basically, some of you, I'm sure, know what some of these technologies are, but they're, for the most part, big data technologies that really make software engineers a lot more powerful. And they're really, really made to be used in the cloud. And then after this, or a layer after this, there's a whole set of companies that work in the cloud that effectively offer managed versions of these types of distributed computing frameworks that you pay for them to manage. So instead of having 3 or 4 or 5 or 10 engineers, for example, standing up an Apache Spark cluster, you can have one engineer just use one of these technologies that effectively manages the service for you and abstracts away some of the difficulty. And so now what this then allowed is that companies can build products that are a lot more powerful, a lot cheaper, and a lot faster. And again, around each one of these companies, these are all now very big companies. These are within the AWS or the Google Cloud or the Microsoft Azure ecosystem. These companies are now so big that they have companies within their ecosystems. So these are just a few companies that would not exist if it were not for the cloud. And the reason they exist is because they could grow very fast when they were very small. And the only reason they could grow very fast when they were very small is that they could do a lot with relatively few people. And the only reason they could do that is because they were using frameworks and managed services that were made for the cloud. So why has the cloud not been adopted for science? So this is something that we've been thinking about, and it's just a really, really interesting question. So I think to begin with, the major use case for scientific computing is MPI, doing fluid simulations across multiple nodes, and those nodes have to have great interconnect. So how the cloud was actually initially architected was that you don't have to have great interconnect. So if you have a process that's running in, say, Uber's backend, Uber's backend infrastructure stack that is responsible for you hailing a cab in Rio de Janeiro, that process does not have to be connected to me hailing a cab here in Urbana-Champaign. Right? There doesn't have to be any communication. You just have to be able to launch identical copies of these processes, and they don't have to talk to each other. So with respect to the poor interconnect issue, cloud GPU clusters recently, with the advent of these very powerful GPUs, have largely fixed this. Because now what has happened is a lot of the tech companies who are the customers of AWS, GCP, and Azure, they want to have great interconnect between GPU nodes so they can do things like model training. There are some perceptions around high costs. And so if you go to AWS or Google Cloud and you put a credit card down, it does look that it's very, very expensive compared to, say, what you could get from an on-premise cluster's IT department. I think this could be fixed with the right business model or right sort of approach to scaling out scientific usage in the cloud. And I think the final point of why the cloud has not been adopted by scientists is that cloud web ops and DevOps or developer operations is just too esoteric. If you look at just the most basic services of these cloud providers, their documentation is 2,000 pages long, and they have 250 managed services. The reason it's so esoteric is because these services are made for companies that have a service or their customers that they reach through the internet. I mean, the name, Amazon Web Service. So there are all these things about networking and security that are just really irrelevant and necessary if you're a scientist. And so what you need is a company that could maybe, or an entity that could come in and abstract away all of that nuisance and minutia. And so what we've built is you can think of it as a science cloud or a research stack. And it's basically a cloud platform built for scientific research. So how you can think of us is we're multiple layers on top of the public clouds, Google, AWS, and Microsoft Azure. And what we're doing is using the public clouds as sources of commodities. And the two major commodities are storage and compute. And so what we have created is basically managed versions of very popular distributed computing frameworks that scientists may find useful, such as OpenMPI for doing simulations, or Apache Spark for doing big data analysis and machine learning at scale. We also go one step further and have science engines. So very popular science packages like Gemstone's Athena++, or Mesa, the stellar structure code, and Flash, the hydrodynamic simulation code. We have managed versions of that work out of the box on our infrastructure. We also have some generative AI capabilities, as well as a managed version of cloud storage, which we call the Stash. So I'll go through what this thing can do for people. But in the meantime, just feel free to ask any questions. I don't know if that's the protocol for these talks. So the user experience for Camber is you can basically think of it as a web service for doing scientific computation. And so you log into Camber, we have a login page, and then you log in, and then you come to this landing page that tells you, okay, what were your last jobs, who's on your team, what kind of, it allows you to search through your data, your stashes. That's our managed version of object storage. Look at your past usage, have a link to documentation. But the real thing is that the real feature is that you can click on Go to Hub. And what Hub is Jupyter Hub. So we have a managed version of Jupyter Hub within Camber that allows you to interact with our infrastructure in a pythonic way. So this is sort of one of our assumptions, is that people in the quantitative world or in the research world, everybody knows at least a little bit of Python. You don't have to be an object a master of object-oriented programming, but you at least know how to do a little bit of Python scripting. And so if you want to, say, spin up an MPI cluster, this is just a simple hello world example, you just say import Camber, and from that, everything sort of follows. So then if you want to do so, say, make compile your C code, for example, it's camber.mpi create job, and the command is make. And so you specify the size of the engine that you want. We have engines that go from 1 CPU core to 2048 CPU cores, and as well as from 1 GPU to 512 high-performance GPUs. And so in that line of code, you create your binary, and in the next line of code, you basically deploy your binary. So let me see if this can work. Okay, so this is a demo of it. So again, the starting point is importing Camber, and then we're going to create our binary. camber.mpi.create, and then you just say command equals make, because that's the actual, as if you're in the bash prompt, that's the command you would actually say. And then instantly, the MPI job is running. So you don't have to wait in a queue, it just kicks off right away. And then once it's complete, you can run your next job, and this is basically deploying the binary onto the infrastructure. And then as you can see, the binary is there in the root directory. And then you can check the status, it's already running. And then we can check the status again. Hopefully soon it will be complete. And then if you want to look at the output, this is the hello world example, just to keep it very simple. And then it just basically prints the output to the local Scratch directory. So no waiting in queues, total Pythonic framework. And it's just there for when you need it. And when you stop doing what you're doing, you don't have to pay. So basically, from a business point of view, it's you pay for what you use. So you weren't paying anything before, and then once you started the simulation or the MPI engine, you pay for that usage, and then when you stop the calculation, you no longer have to pay. You have a question?
So the question was, it wasn't clear to me, like how you say no waiting for the queue.
There's no queue.
If it's designed like that.
We have enough on reserve. So what we basically are trying to do is give a cloud-like experience. This is one of the elements of what we're trying to do. We're trying to give a cloud-like. We're trying to see if people want to have a cloud-like experience, which means that you're taking advantage of the main feature of the cloud. The main feature of the cloud is that it's infinite. That's why I showed that gigantic data center. That is the central feature of the cloud. It's infinite. So because it's infinite, there is effectively an infinite amount of resources on reserve. And so what we've done is we've what's called containerized MPI to work efficiently with our infrastructure so that when you want to spin up an MPI cluster of anywhere from 1 to 2048 cores, we have the infrastructure ready to create that MPI cluster in a few seconds. Yeah, sure.
I'm curious, what if I have a job that need to run for like a week?
Yeah.
Is it okay? And because I see you show that is a Jupyter notebook-like environment something,
yeah.
I suppose I will need to like let the page open for like a week. Is it the case? Or?
Yeah. Yeah, so you can log out and it'll be running in the background.
Okay.
Yeah. Does that answer your question?
Yeah. Thank you.
Mm-hmm. Yeah, hi.
So I just wanted to drill down to make sure I understood. When you say there's no queue, you mean there's no person that may be ahead of you. Are you distinguishing that from there possibly being a wait time?
The wait time is just the time it takes for us to spin up the container.
Okay, so spinning up so it's constantly over-provisioned. Everything is spinning right now. You've got a cluster that you're personally managing. Okay, thank you.
Yes, yeah. So the underlying technology that we're using right now to manage the cluster, because we're a small team, is Kubernetes, which is a container orchestration framework. I think as we hopefully get bigger, we'll probably spin something distinct for ourselves. Anything else? Okay. Yeah, sure.
So when you say you have enough node, do you mean that you are renting nodes from Amazon, Google, or you have a physical node on your own, and how large it is?
Yeah. So again, so we are renting. Well, I mean, we're paying. I mean, we're paying from the cloud providers their underlying compute hardware, and then in terms of the question, how much do we have? Infinite, because the cloud is infinite. Yeah. So, I mean, I don't know how, that's actually the case. As much as the cloud has. So, and since they really haven't ran into limitations, there is a limitation in the cloud. So, there's a little sidebar. So, for GPUs, for the high-end GPUs, the NVIDIA A100s, and nodes that run the NVIDIA H100s, which are like the cool, fast, super powerful GPUs, which we'll actually show an example of that later. The demand for those are so high that NVIDIA cannot produce them fast enough, and the cloud cannot buy them fast enough. And it's because of all this ChatGPT stuff, right? That you actually have to reserve those in advance. So there's no, for the A100s and H100s right now, there's no on-demand experience. You have to reserve it 24 hours in advance. And you can actually only, the most we've ever been able to reserve are 8 nodes at a time, which is 64 H100 GPU cards at a time, because there's so much demand for them. And that's why NVIDIA stock is gone crazy, basically. So, okay. So thank you for those questions. So,
another question?
Yeah, sure. Hi.
So always a risk with using the cloud is that something might run much longer than expected.
I imagine this is a sort of thing that you would have built in, but do you have, are there ways that users who are developing new tasks can protect themselves from like infinite loops or things that run much longer than they planned?
Yeah. So basically we have protections for that. And also there's a dashboard, a landing page dashboard where you can see what jobs of yours are running. So, if there's only so much damage that you can do to yourself in maybe 24 hours. So if you just log into right now your own dashboard, you can see what's been running. And if you don't want that to run anymore, you can kill it. We also have in some of our APIs for some of our engines the ability to actually cap how long it's going to run. Yeah. And and there's some other safety features like that too. So great. So okay, a little bit of I hope that gave a little bit of a background of what we're doing. So now maybe a little bit into why we're doing it. So our belief is that, number one, globally, I think this is not really bad, it's true. Globally, many people in the world are excluded from computational sciences. Just basically because they either live in a place that's not that rich, or they live in a place that doesn't have people who have been trained in computational sciences, okay? We also think that, the second belief is that science, and look, I'm no longer a scientist, but from what I remember about being a scientist, is science will greatly benefit if number one is fixed, okay? And so, just to get, my parents are from India, they actually grew up in villages. They're both farmers, in their respective villages. They went to college and got a technical training back, so you can go through college back then and just have textbooks, got technical training. They came here and I'm here giving you guys this talk, right? So, but there's no reason, if their version of themselves today were in India, that they would not be able to do computational sciences from an intellectual point of view. There's nothing I see that would prevent that. But all those people in India, all these people in Africa, all these people in South America, a lot of people here in the United States do not have access to this. And it's a great disadvantage to them, and I think it's a great disadvantage to science. So that's our second belief. Now, our third belief, because we are a business, is that fixing one is a good business strategy for us. Because, quite frankly, if we can fix one, then we have a lot of interested users who are using our platform, whose careers are going to grow because they're going to be successful scientists, and that they're going to use us for a long time. So this is one of these rare examples where maybe, to put it crassly, capitalism, I know that's a bad word, and doing good are aligned. So I hope my investors did not see. This is being recorded? I did not see that. Okay. So in terms of education, so our first customer is the University of Wisconsin-Milwaukee, and they've been using Camber for their second summer. So there's a NSF-funded summer school hosted by Phil Chang, who's the department chair, who's a really good friend of mine. I went to Santa Barbara with him, really smart guy. And basically, they have a summer school for 25 students in the local Milwaukee area. They're grad students. And all the curriculum is in Camber. Okay, so, and what is in the curriculum? It's big data, machine learning, high performance computing, introduction to large language models. All the coursework is in 4 weeks. And then the last 3 weeks, they do project and then show off their projects. So I think this is a very, very, very interesting sort of, this is actually, I was in the back here, I took, that is Chang up there. I took a photo of this happening. It was very exciting first time in Milwaukee in June. And it was really great to see that in action. So recently there's an Astrobytes article that featured Camber. And what we're putting together in conjunction with Astrobytes as well as the AAS, the IAU and other organizations is an international computational astrophysics scholarship for up to 100 students in the first year, where we will give them some capacity of Camber, some upfront capacity of Camber, and it will be funded in part by private foundations. So the role that Astrobytes is actually playing is helping us shape what are the contours of the scholarship, really understanding what the needs of graduate students throughout the world are, and maybe even making some type of curriculum for said people. Okay, so what else can you do with Camber? I think this is sort of follows from this sort of like democratization point of view. Camber makes it, from my perspective, very easy to work with very large publicly available data sets. So this is an example, and you could go to our webpage and we have a tutorial on how to work with Gaia data in Camber. So again, the starting point is importing Camber, okay, once you've logged in. And then after that, you instantiate what's called a Spark cluster. So Apache Spark is a big data technology that is very, very, very commonly used in the tech sector. And what it's really done for is doing data engineering and doing basically sorts and joins and group bys on data sets that are several gigabytes to several terabytes in size. And the nice thing about Apache Spark is that it has a really good API for Python. And it's sort of, you can kind of start using it and get used to it in a couple weeks. And I've actually seen this. I've had interns, college interns on my teams in the tech sector who don't even know Python, don't even know SQL. But in 2 or 3 weeks, we were up to having them do like relatively sophisticated things with Apache Spark with an API similar to this. So again, the starting point is you import Camber. And then to instantiate a Spark cluster, it's just, again, one line of code. And then we have something called the Open Stash. So the Stash is Camber's version of cloud storage. So if you're familiar with AWS, the cloud storage in AWS would be Amazon S3. If you're familiar with Microsoft Azure, their version of cloud storage is called blob storage. And so our Stash is our version of that. And so we have stored the Gaia data set, data release in the Open Stash. And so the Open Stash is basically, it allows anybody who has an account with Camber to view that data set. So you don't have to pay for it, it's just there, okay? And so we're gonna load that data set, the entire Gaia catalog, it's billions and billions of stars, right? We're gonna load that into a Spark cluster from the Open Stash and have an API around that Spark cluster that's called the data frame, which I'm sure all of you are familiar with. And then with that data frame, we're going to make a histogram. I'm not showing you what the code behind that histogram function, but it's pretty standard stuff. And then from that, in about 3, 4, 5 minutes, with a Spark cluster with an engine size large, we were able to sort the billions and billions and billions of stars in this terabyte of data in a few minutes. And so this is the all-sky map of these stars. It's basically a sort and right ascension and declination. That's like coordinates, right? It's kind of rusty here. So we did this massive two-dimensional sort in a few minutes. This is the all-sky map of Gaia. The yellow pixels have 100,000 stars in them. So, and then the interesting thing is once you've done the sort, you can store the sorted output in your personal stash. And then when you want to interact it with it again, you don't have to sort it. And you can just then make this in seconds rather than minutes. OK, great. Sure.
What are the data sizes for that? Now, are there any financial ramifications
Yeah.
for example, that data set that you brought in? And if you want to store it, how much does that?
Yeah.
Is that an extra cost on top of the payment that a researcher or the project would have to provide?
Great question. Thank you. So let's get down to brass tacks here. So in terms of how we make money, our current business model is that for every time you use one of our engines, you pay for that by the hour. So, and the amount that you pay is proportional to the size of the engine. So a small engine is twice as much computational power as an extra small engine, and a medium engine has twice as much computational power as a small engine, so on and so forth. And so a medium engine, you pay twice as much by the hour than a small engine. Now, for storage, for anything in the OpenStash, that's the publicly available stuff, our customers don't have to pay for that. That's just part of the service. Now, you have your own private stash, right? And so you pay for data in the private stash. And the cost for that are $23 for what's called hot access to it, where you can access it at any time you want, as much as you want. That's $23 a terabyte per month. And then if you want to have less access, if you want to start iceboxing some of that data, then that can go down by a factor of 100, depending on how much you want to icebox that data. Now, that cost, $23 per terabyte per month, I confidently say that because that's the price we pay the underlying cloud provider. So we don't make money on that. So, yeah, great question, though. Yep. OK, so you're all, everybody here is an astrophysicist, right? So no, me neither. So we have another managed engine. So we have about 6 or 7 managed engines, assigned like astrophysics engines in here. So one of them is Mesa for computing stellar structure. Okay, so I don't know if any of you have used Mesa. I've tried to use it. I found it kind of difficult. And when we are doing what's called customer discovery and talking to graduate students and postdocs from, institutions where we have friends at who allow us to talk to people, a lot of things that we heard is like, look, Mesa is kind of hard to use, but we all have to use it because we all have to do something with stars. So this is in Camber. If you want to calculate the structure of a star, this is what you have to do. You have to import Camber. And then one line of code, we call this star job, right? Camber.mesa create job. And then it just runs. And the input file is just in the local root directory that says what's the initial mass and the metallicity and so on and so forth. And this just runs. So let's see if I can get this. Let's create the sun in a minute. Maybe 2 minutes. Well, because we did it for the Hubble time. So if you did it for 6 gigayears, it's a minute. So this is us, creating a 1 solar mass star in Mesa. And so, you import Camber, camber.mesa create job, and the command is just make and run. So you could actually log into Camber right now and do this. This is in our tutorials. It's in our documentation. I'm just going through our tutorials right here. And then you can check on the job status. It's running. So again, no waiting in queues right here. So it's all, we've effectively containerized Mesa, so it could just start running like that. And yeah, you just wait, to 14 gigayears, which is the Hubble time, right? So that takes like 2.5, 3 minutes for this to do it. But to 6 gigayears, it's about a minute. So, and let me just fast forward to the answer. So yeah, you can check on the job status. And as you can see on the left, your log outputs and so on and so forth, if you want to do data analysis, they get created there in your local root. It also gets mirrored into your own personal stash for long-term storage, if you like as well. So yeah, I think we're making something here. A star, yeah. So we have a little applying routine, and it keeps. Yeah, that last few gig years really takes a long time. But anyways, as you can see, you can calculate the structure of a star in a couple minutes without having to mess around with the SDK. You don't have to mess around with Fortran compilers. It just works right out of the box. Another interesting feature about doing this in the cloud is that you can run multiple versions of this at once. So you can basically run thousands of stars, and we have in one of our tutorials how you can run multiple stars at once on demand. So if you figured out how to do that on an on-premise cluster, you would have to often put each job, star job, into a queue, and then you'd have to wait for them to sequentially, execute. And it could be that if that queue has a lot of things packed into it, you could wait. The delta t of the waiting time between jobs could be longer than the delta t of the job itself. So what we are basically taking advantage of, as you've had me point out, the infinite capacity of the cloud is that you can run multiple jobs at once all at the same time. So you can do parameter sweeps. So if you want to run 1,000 stars all at once, you could, in Camber, actually do that in minutes. So, yeah. Okay.
So I see that you have Mesa and Athena already implemented in Camber.
Yeah.
My question is how easy it is for Camber to ingest other very popular codes,
Yeah.
and what are your next plans to incorporate such codes?
Okay, so with our current crew, which is me, who just talks. We have a science advisor, a technical science advisor, Shane Davis, and then we have a 3-person engineering team, including one of my co-founders. With that team, it takes about a month, but that's with us doing a whole. We got other stuff that's going on, so it takes about a month to do. So that's not scalable. And also, that's not very democratic, right? So what we are, on our roadmap, I think not in the next few months, but maybe in the next year, is going to have the ability for somebody to self-serve. So where there's an API in Camber that allows you to effectively, create a Docker image or an image, right? You don't have to know what Docker is, but effectively, what a Docker image is a tar file, right? So you basically put a bunch of packages and the locations of where to upload packages, and then specify the API, in the Camber dot whatever your engine is, which we constrain, right? And then you submit that to us for approval, and if it works and it looks like it conforms to the standards of what we would expect to be in the platform, then we'll publish it, and we'll make that part of our API documentation and reference. So that if you want to have, if you are a code developer, so that's the minority of the population, right? If you are a code developer or a code publisher, and if one of your desires is to have many people be able to use your code, this is a way to do that. Gentleman in the back, yeah. That's you, yeah.
So I wanted to ask, I see you've got the engine here. It's aware of the fact that problems have to be compiled into Athena at start time or at build time and so on. I wanted to ask how much information does it have about Athena with respect to the stash? Is it aware of the specific file patterns that indicate an Athena output? The same thing for Mesa and so on. Does it know, can I just stash by output, or do I have to know my file naming pattern and so on and supply that to the stash? Yeah,
so basically it's how we've architected it right now, and this might change. And I think it should change, but this is, we have to make decisions as groups, right? So, but how we've architected it right now is that we have a mirror of your local scratch. So your local scratch is the local file system, okay? So right now, I'll tell you some of our secrets, right? Right now, our local file system, we're running Lustre. Okay, that was actually quite hard to figure out how to do, like how to get Lustre to work in the cloud. So basically the local file system is Lustre, a Lustre file system. And so what we're doing is every time a piece of information is put on the Lustre file system in your local portion of that file system, that container is mounted on, right? Which is we wrap around in this thing called the engine that has this interface, right? Every time a piece of data is written there, right, it gets beamed and mirrored into the stash. And the stash is an object store. It's not a file, it's not something you mount a runtime onto. So we're kind of still working on like how that's going to work. But really, and I'll say this at the end, like we need people's input, like what's the workflow that works best for everybody. So I hope that answered your question. Yeah. Go ahead.
So what if I want to do some more deeper modify? For example, I want to modify the Mesa, modify evolution something, or I want to like modify equation of state in Flash something.
Yeah.
Will it work?
Yeah. So one thing that a lot of the Mesa power users have told us is like, okay, this is great, but I want to run my own branch or version of Mesa. So say you want to, and this is getting into the weeds a little, okay, and maybe if I take a step back, right? So what are we doing here actually? Okay, what is the sort of insight that we're having here? Fundamentally what you're doing is you're solving the equations of physics. You know, whether that's in chemistry and whether or not it's in molecular dynamics, it's some laws of effective field theory of physics, right? So what you're doing is F equals ma. I mean, that's it, right? So the integrator, whatever it is that you're doing, it's really how it writes it, the integrator or how you set up the problem is really ma equals f. And so you're time stepping, right? You're multiplying by delta t to get what the next time step is. Okay, so the f is some differential operator, right? And so what you're doing in all these simulation packages is you're creating some type of runtime, some type of binary that's doing this process, right? Now, that's one thing. Now, the other thing in F equals ma is that the F has constants in it. So if it's electrostatics, it's like the epsilon naught, permeability, emissivity, whatever it's called. The epsilon naught and the mu naughts, and then there's the charge. So those are things that you go out and measure, right? So in Mesa, the equivalent of the mass and the epsilon naught and mu naught and so on and so forth is the opacity tables. Right? That's something that's computed somewhere else. That's just some input that you put in here. Or the equation of state. That's something that is computed somewhere else that's put in here. And then the differential operator is just a differential operator. So you may want to customize the differential operator. You may want to customize the opacity tables, right? As long as your customization is not that different such that the dependencies do not change from what we have in Camber.mesa, then it should run. Now, how you go about doing that is, that's a technical detail. We can talk about that if you want to use it. If you want to, for Mesa, if we want to get into the weeds, there's an F90 file. You can just pull in a different F90 file. You can go into that F90 file and you can modify it. The opacity tables, what you can do is upload a different opacity table into the stash and then mirror that into the local scratch. So there's a lot of ways that we can do it. But we want people to use it more for us to be able to know exactly how to do that for everybody optimally. Does that answer your questions? Kind of? Okay, we can talk later then. Okay. Yeah, sure. Yeah.
So I had a few questions, and it was kind of about your answer to UA earlier. So a lot of software in astronomy is open source. It's free to use, it's free to download, free to modify. And that's how you could load these programs into Camber.
Yeah.
And I guess your answer saying that, like if you want your software to be used by a lot of people, talk to you, try to get it uploaded to Camber. And it's kind of a little bit of problem with that. It's kind of, I want to make sure you're kind of not saying like, oh, if I want my astronomy software to be used, you're going to have people to pay in order to use the software, right, by loading it onto Camber.
Yeah, so say let's take this example. Camber. We can just talk about the whole business process of this, right? Okay, is that what you want me to elucidate here?
I'm just kind
I
of.
think so, right?
I'm just unsure about having software loaded directly onto Camber versus having a user load their own software.
Oh, yeah. So actually, so we have here the latest version of Athena, okay? Now, you could actually git clone the latest version of Athena right to your local directory, and it wouldn't make a difference. It would still run both versions, which are the identical versions, right? Now, if you want to modify this code, so the code Athena here is not hidden. It's literally right in your local directory. So when you instantiate this import camber.athena, it will appear in your local directory. Okay. And so does that answer your question?
Sort of. I think it was more about the business model. I think we can
Okay, so then in terms of the business model, so Jim Stone is not making a penny from us doing this, okay? So this is an open source piece of software, right? And what we just had to do is we're talking to people and they're like, oh, like this is kind of hard for me to use. That's kind of hard for me to use. So then we said to ourselves is like, aha, not just managed infrastructure, not just like MPI or Apache Spark or something like that, but actually a managed science engine. So like actually running that package on infrastructure, they don't actually have to worry about that. Now I think somebody asked a question like, how many can you do in a year, right? So we can do with our current crew maybe 10. So if we hire more in November, December, January, maybe we can do 15. But we're going to get pulled in other directions too. So that's not scalable. So what we are going to work towards is such that anybody who creates a science code base that they want the public to use can make a camber.your package and then publish it in Camber, and then that becomes available for anybody to use on our infrastructure.
Is that service free?
No, because the infrastructure is not free, because we have to rent it from AWS. Yeah.
Okay.
So
is it free to publish the work?
Yeah, it's free to publish the work. Yeah.
Okay.
Absolutely free to publish the work, because that's the incentive. The incentive is for us to make that as free and friction-free as possible, right? Because in terms of our mission, we want as many people to be using this as possible, right? So if there's a piece of code that somebody wants to use on a piece of infrastructure but can't because they don't have the infrastructure, or if they do have access to infrastructure, they don't have the IT support around them to run it, we're going to get rid of those barriers. But then also from sort of a business point of view, it's that publisher of the code then can tell people, hey, you can use my stuff easily in Camber. So it's sort of an alignment there. Go ahead. Hi.
So if I understand your business model, your cost essentially is probably dominated by what AWS charges.
Yeah.
And
what we negotiate with.
Yeah, and then you've got some staff, development staff, and so on, and then some profit on top of that. Mm-hmm. And you've gotten these fellowships to sort of democratize access, so that'll pay for, you said 100 people a year or something like that?
Yeah.
But the long-term goal is that, for instance, PIs would allocate part of their grants to pay for this.
Yeah. So scientific research, great question. And this is asked by every venture capitalist I talk to. So scientific research happens in two places. It happens in academia, and it happens in industry. Okay, there's a lot. And actually, in terms of the compute, from our initial market research, the majority of the dollars spent are actually in industry. Like Boeing spends a lot of money looking at turbulence on like a wing.
Sure, yeah.
Like that. So that's one thing to think about. So that's just normal business. Now,
sure.
In academia, our go-to market strategy, which is like terminology, like how do you kind of get people to start using your stuff and making money from it? our initial go-to-market strategy from inception is to have a strong footprint in academia. And that's a little bit unique of Camber, and that's a bit informed by my background, so on and so forth. So then the question is, how do you make money in academia?
Yeah.
And so people who are paying, so the sources of money are the people who can write checks, are PIs. So some PIs are writing us, money.
Personal
grant.
checks.
No, money from their grants.
Right. Okay.
Yeah, money from
So
their grants.
that-
And then there's IT department. So we actually have one institutional IT department, the Institute for Advanced Study. Their IT department comes from the chief information officer. They're writing. That's the check writer in that case. So our go-to-market strategy is basically get people to use it, then PIs, and then.
Well, so my question was, at least in the academic context, what kind of interaction have you had with the funding agencies? And are they willing to support this business model?
I haven't talked to them yet.
Okay. So at this moment, I don't know, for example, if I could write a proposal for next year, for instance, asking for Camber money.
Oh, you can. So,
Okay.
and people have. Yeah, and people have. So, the NSF funded, so we're being, out of grants, we're being funded from the NSF and NASA. A Hubble Fellow actually uses us, and the Hubble Fellowship stipend actually went to Camber. So it's just software. So basically, in any grant, you can allocate software expenses, and it's just a software expenditure. Just like Microsoft Word, that's a cloud service.
The subscription, yeah, okay.
Yeah, but it's a cloud service, so it's just our business model is not. It's a little bit different, because it's capacity, but we can work with anybody with that. Does that answer your question?
Yeah, thanks.
Okay, great, thank you. Yeah.
So this is going to sound like I'm challenging you, but I want to preface this by saying that I'm coming at this from, internal to an institution that includes among its many different efforts the provisioning and creation of infrastructure for scientists across the nation, for instance. So I wanted to ask, you said that Camber is unique in that it uses academia as a foothold into industry. I don't think that's unique. NVIDIA's been doing this for a long time where they showcase, this is all the cool results that we get from using academic codes, and then they sell their stuff to industry. And it's so, yes, I can give you examples of blog posts where they show we did this amazing, flop speed up on the Enzo code 15 years ago. Isn't that great? Now come buy our stuff for fluid dynamics behind the wall.
Oh, okay.
So
that's weird. Yeah.
I mean, it makes sense. But what I want to get at here is right now, the interests of scientific research, as you mentioned, in one of the 3 bullet points that you had at the beginning, poor interconnect between nodes has been largely fixed because now people want to do, AI on tightly interconnected cloud GPUs. So it happens that scientific research's interests align with the private industry's research, and so we're benefiting from that. I wanted to know what.
Yeah,
well,
yeah,
no,
yeah,
I mean, that is.
Yeah, I see where you're coming from.
So, what, and you said a lot of science happens in private industry.
Yeah.
What happens if the interests of private industry no longer continue to align with the interests of astronomical research? What if everyone moves to 16-bit floating point numbers or something like that, which is a big push right now? How is our reliance on Camber going to be shifted?
Well, I mean,
in that instance?
I haven't thought that far ahead. I mean, when we get that far ahead, those will be good problems. Maybe, I guess one way to think about it is if Camber, so what we're doing is how to view us as an IT provider, right? We're not a science organization. We're an IT provider, right? We're like AWS. But what the current incumbent is basically a panoply of companies like Hewlett-Packard, Dell, so on. So those are the people who you're buying these server racks from, the hardware from, as well as. Pardon me?
I apply for exceed time.
Yeah, so you're not if you're applying for exceed time, you're not seeing the business side of it, right? That thing that you're putting your code on was bought by somebody somewhere from someone. That's where we're coming in. So we are replacing Hewlett-Packard, we are replacing Lenovo, that's what we're trying to do is the incumbents of how it's being used from an IT technology point of view, that's what we're replacing. So in a wonderful world for us, it would be like when you apply for exceed time, you can apply for exceed time on on some of these big clusters. I forgot their names. Delta. Okay, Delta.
Jetstream, which is the cloud.
Okay, so you can apply for that, but you can also apply for Camber credits. And then you can transfer the Camber credits that are in the account of the NSF or some program officer at the NSF to your local university, and then that disperses to you. Yeah. So yeah, that's the layer that we're at.
Thank you.
Yeah. But I think the differentiator compared to something like Hewlett-Packard or Dell is that we're making a product directly for scientists to use, right? And so we're interfacing with you directly and trying to make the product good for you directly. Go ahead.
Yeah, it seems to me, not HP or Lenovo, but Access actually is maybe the better analogy. And no, that's okay. Anyway, so I mean, Access, you apply to Access for credits that you then can spend on different machines. And it just so happens that Access has one customer, which is the paying customer, which is NSF.
Yeah.
And so I guess one question would, so your model is more paying from the users rather than paying from a single entity like that.
No. So the business model that we're using, which is this upfront capacity payment, and then you drain down by usage. We stole this from a couple other companies. So there's two companies, Snowflake and Databricks, right? Which are basically managed. You can think of it. One's a managed Apache Spark for tech companies, and one's a managed database. So what you do there is you buy.
Well, actually, I mean, using mainframe providers in 1968 probably would have charged the same way. Right?
Okay, yeah. So I didn't work with them though. Yeah. How it works is if you're like at a big company, like say Capital One, right? Capital One is like some big bank, right? And when Snowflake had a initial public offering, they had to list like what their biggest customers and the client size. So that's always embarrassing for some of these companies because they have these embarrassingly large companies that are spending way too much on them. So Capital One is spending, I think at the time that Snowflake filed for public offering, $30 million a year on Snowflake. And so how that works is the head of IT talks to the head of finance there and is like, okay, we have to buy this much capacity in Snowflake for the next year. They negotiate between themselves, maybe get the CEO involved, and then they tell Snowflake, okay, we're going to buy this much up front. And then that's one person who's writing the check, and then in Capital One, there's probably like 200 people who are using it that are associated with that account. So in this vein, what you would do is be able to transfer credits from one account to another account. Mm-hmm. And then the holder of that account can then disperse within, say, their university.
Okay. In the interest of time, I'll ask later. Yeah,
okay,
thanks.
Great. So just one more thing. Thank you for all the questions. I really appreciate it. So you can do some sophisticated things with Camber. Sophisticated things that can be used to do some pretty powerful calculations. So again, this is built, Athena K, which is the kind of experimental version of the Athena code, Athena++ code, that works on GPU. So we're going to do the Kelvin-Helmholtz instability. And when I show this to venture capitalists, they're like, what the hell is that? But I think this is one of these audience where everybody knows what it is. So we ran this on parallel on 8 H100 GPUs. The resolution is 8192 squared. Again, it's the Kelvin-Helmholtz instability. This took 3 hours to run. In terms of computational equivalent power, it's equivalent to 10,000 CPU cores, which is kind of the largest computation you can run on any on-premise cluster at a university. And this costs $200. So I think this is sort of kind of exciting, what you can do with GPUs. And the cloud has a lot of GPUs, again, because of their buying power. So if you want to experiment with with GPU code, this is kind of an interesting place to do that. So okay, so just one last thing is, I am not here to sell. I am here for your input, okay? So we need your input, okay? So we're starting out, and what we need is for people to give us feedback on really what you want. And if you tell us what you want, we will build it, okay? And that's just the stage of our company right now. So you can go to our website, you can create a free trial, you get $100 of usage for free. $1 of usage equals 1 Camber credit, that's what we call it. And what we're asking for is, like, what kind of tools, do you want to see? What kind of science engines would you like to see? What kind of data sets would you like to have in there? And if you could snap your fingers and do what you wanted to do, we'd love to know what that is. I'm not saying we know how to do it, but it'd be good to know. So anyways, reach out to me, Aristotle at cambercloud.com, and I'm happy to take any questions and connect with you. So thank you.